All right, so now that we have done alternating series error bound, we're going to go ahead and learn about Lagrange error bound, which is going to work for the rest of the series that we talk about. So if you guys recall, when we evaluate a function, that is, in the term of series, that would be finding the sum of an infinite series. That would be every single term you could possibly find. So that means that if we cut the series down, if we only look at maybe like, let's say the first 9 terms or something, then the rest of the series, the 10th term on to the infinite term, that would be the remainder of what we did not find. That would be how far off our answer is. That would be the error of our answer. So when they talk about the remainder theorem and when they call it error bound, that's why it makes sense. It's saying the remainder of the series is how far off our answer is. It's the error of our answer. So when we look for the Lagrange error, we're going to do just like alternating series where we look at the next term. So if we have a 5th degree polynomial, then we're going to look for the 6th. Not term, but like the next degree up, I guess. And if you think about how you would have created that term, you would have done the derivative multiplied by x minus whatever the center is, so maybe x minus 1 if it was centered at 1, and then you'd have it over to the 6 factorial. If you were doing like, back to that example of maybe we had a 5th degree problem, so this would have been a 6. The big difference here is we start talking about the max of the derivative on a specific interval. So I'll talk about that more in a second. So up until the time of Lagrange, people were using these approximations and they said, man, like they're good enough, they're pretty good. And Lagrange came by and he said, like, I want to know how good they are. I want to be able to quantify how good my answer is. And that's what the error is doing, is that the smaller the error, the more accurate the answer, and you can quantify that. You can say that your answer is better because it's not as far off of the true value. So let's go ahead and kind of get going with this. So this is the formula. I'm going to kind of talk through it with this. Maybe I'll talk through it here. So if we were to think of a problem, and like I said, we were doing the 5th degree polynomial. So that means that our error is based off of the 6th derivative. And maybe the center of our graph is at 0, but we're evaluating it at 1. Whenever we do the error bound, we always want to kind of err on the side of caution. You know, we want to have conservative estimates because we want our error bound to be like an accurate representation of how far off our answer is. So when they talk about this, like the value of the derivative, they say if we're centered at 0 and we're evaluating it at 1, then instead of just looking at what the derivative is at 0, look at the derivative and the value of it on that whole interval from 0 to 1 and see if maybe there's some bigger number there. And if it is, use that bigger number, because a bigger number would multiply in this and make the error a little bit larger, which would make the error more accurate. So as soon as you say, okay, my answer could be off by a little bit more, now you're being a little bit conservative with, saying that your answer is right or not. So that's basically all this is doing, but the rest of it, like I said earlier, is the same as an alternating series error bound. So sometimes when you have this part where you have to find the max of the derivative on the interval, sometimes it could be given to you in the problem. They'll just straight up tell you what number to use. Sometimes they'll give you a graph to look at. Sometimes they'll give you a table to look at. Or sometimes it could be a function that is familiar enough to us that we could pick the value ourselves. So if we look at example number 1, this is a problem where they give you the value already. They don't give you a picture of a graph. They don't give you a table. They just tell you the 5th derivative is less than 0.3. That's a maximum value. That's the only information you have, so you're going to have to use it that way. Okay, so here they say we're looking on the interval from 2 to 3. The center is 2. We are evaluating the function for 3, so that's how that interval came to be, 2 to 3. Centered at 2, evaluated at 3. And they wanted to know how accurate the approximation is if we're using a 4th degree Taylor polynomial. So when we write error, we were writing the word error for this, but if you want to look at what the error actually is, it's saying if I were to take the function and evaluate it at 3 and subtract off my approximation, the error is how far off my answer is from the approximation, all right? Or it's the remainder. If I were to plug in my approximation, it's how much further I would have had to go to get the actual value. So that is less than or equal to the max of the fifth derivative. So it's the fourth degree. So that means it would be the fifth derivative on the interval from 2 to 3. So from the center, which was 2, to 3, which was the value that we were evaluating. And then times, and then we write the rest of it of what it would have taken to write that term, right? So we always had the derivative times x minus the center. Then the exponent was the same as the derivative that we were on, divided by the number of the derivative factorial. That's how we came up with each of our individual terms. So the amount of error that we have is, and then they gave us the number to use, is 0.3 times, and then I'll go ahead and plug the number in for x. 3 minus 2 to the fifth over 5 factorial, which is 0.0025. Okay. They want us to use this answer to determine the interval that the evaluation should be in if this was the approximate value. So we're going to say, okay, if we want to know what the actual value is, 1.763 minus 0.0025, and then plus. So the actual value of the evaluation should be in between 1.7605 and 1.7655. Could it be 1.768? No, 1.768 would be outside the interval. It's outside the interval. 1.761, yep, that's right, inside the interval. All right. Next example, we want to find the fifth degree Maclaurin polynomial for sine and then use that to approximate sine of 1. So the Maclaurin polynomial, fifth degree would be x minus x to the third over 3 factorial plus x to the fifth over 5 factorial. And that is, I'm plugging in 1. So that's 1 minus 1 over 6 plus 1 over 120, right? Because 3 factorial is 6 and 5 factorial is 120. Just going to go ahead and I'm giving 5 decimal places because I know that with the error they asked for 5 decimal places, but I guess that didn't really matter. Now they want us to use the Lagrange error bound to find the maximum error for our approximation. So we're going to say the actual value of sine of 1 minus our approximation is how far off our answer is. And we're going to find the max. If this is 5, we're going to do of the 6th derivative on, and it was centered at 0, but we were plugging in 1, so the interval we're using is 0, 1. And we're going to multiply that by x to the 6th over 6 factorial. Now, if you're paying attention to this, this is an alternating series, so we could have done this problem yesterday. And if we did this problem yesterday, we would have just used the next term, x to the 7th over 7 factorial. And I talked to a friend of mine who is an AP grader, so she goes to whatever state it is, and after the AP exam is over, she hangs out with all the other calculus teachers and helps grade the FRQs. And she said that based on this definition, using a 6 is fine, but based on what we know about alternating series and the Maclaurin polynomials, x to the 7 would be fine as well. Both of them would get full credit on the FRQ for that. So just a heads up there, I'm going to go ahead and use the 6 because I think that it makes a little bit more sense to just, specifically add 1. especially if we look back at our notes later to see that it added 1. But you could also use the x to the 7th and still be correct. So for this next part, they did not give us a value to use. So up here, they told us what value to use for the max for the derivative. Here they did not. So what I'm going to do is I'm going to go ahead and write out the original function was sine, and then I'm going to go all the way to my 6th derivative just to see which function I'm talking about, because if I don't have a specific value or a table or a graph, that means I have to come up with the graph myself. So derivative of sine is cos, and then negative sine, negative cos, positive sine, positive cos, negative sine. So that means what we're doing is we're picturing a sine graph, and we're picturing this sine graph on the interval from 0 to 1. So what I did is I went ahead and printed out a graph. This is a negative sine curve. We're looking on the interval from 0 to 1. And if I look, I can see that sine of 1, or negative sine of 1 is the biggest value there if we think of it in terms of absolute value. So sine of 0 is 0, and then the numbers get bigger and bigger and bigger until we get down here. Because the size of the number is bigger. So this is probably about 0.85, but the common practice with sine and cosine is to just use 1. And the reason for that is that sine and cosine graphs bounce back and forth between positive 1 and negative 1. And so if you always use 1 for that, then you never have to graph it, and you just always know it's a conservative number because it's bigger than what it would have been anyway. So we're going to go ahead and use 1 there because we're, thinking about maybe I'm trying to do this portion of the problem without using a calculator or something. So I'm going to go ahead and use a 1, but if you wanted to plug in negative sine of 1, since this is a calculator active problem, and then use that decimal, you're welcome to do that as well. Both of those, again, would be accurate answers. That was also something I clarified with my friend. So I'm going to say the error, and I could use 1 right here, or I could use 0.84 right there. It doesn't matter. I'm going to go ahead and use 1 because it's easier to plug in. And so the error is less than 1 divided by 6 factorial. I don't know what that one is. So 0.00139. Okay, so this is a good error bound for the problem. You could plug in negative point, like you could use this number right here. That would be a good error for the problem. You could have used 1 divided by 7 factorial. That would have been an okay error for the problem as well. So all of those are good, and that would be something where the FRQ would maybe say one of those answers was correct, but the AP grader just knows that when they grade that they would give some more answers for that one. All right, let's go ahead and look at the next part of this. So still referring to the same problem, use your answer to find an interval such that sine of 1 has to be on the interval. So what we're going to do is we have that original answer. I probably should have saved it. So I'm going to go ahead and store this as my approximation. And then I'm going to go ahead, grab this, store this as my error. So my approximation plus the error. And then approximation minus the error. Okay, so we think that sine of 1 is somewhere in between those two decimals. Could sine of 1 be 0.87? No, it's not on the interval. And we are reasonably, our answer should be right. So, all right, example 3. I think I'm going to go ahead and leave this one for tomorrow so we can do this one together in class.